Hi, this is team Stop Forest Fire at Any Cost. In our team, we have Taylor, Joshua, Sammy, and myself, Arpit. Today, we will cover the assignment's overall goal, the data we have collected, and then discuss the project in detail, including what we have covered and how it adds value to our goal. Our project goal is to analyze the impact of forest fire on United States economy and environment and sensitize the audience to the impact we can have by reducing the burn days on the economy and the environment. To analyze the goal, we have investigated the primary cause of forest fires in the US, that is natural causes or human related causes. We have looked at the cost per acre burned, suppression cost, and the land loss over the years to understand which cause has more financial impact. To understand the environmental impact, we have looked into the acres burned and burn days. Now I hand it over to my teammates to talk through each component of our project.
For this project, we decided to explore human-caused and nature-caused fires over the past 37 years. To the right of the map, you can see two pie charts that display the burn days and acres burned for a given year, caused by either natural causes or human caused. There's an animation that cycles through all of the years on its own. But if you choose to stop animation, you can also manually slide through each of the years to glean your own insights.
Additionally, in our introduction page, we also have two clocks, ones that measure the current acres that are being burned and also the reforestation clock. An important key note is that an associated feature that is generally spoken with when it comes to acres burned is the CO2 that's emitted. And so that's why our team decided to go ahead and add the reforestation clock. In addition, we added a feature to where the user can implement a number that is illustrated in the millions to see how the reforestation clock equates to the acres burned.
So, our exploration goes into the impact of wildfires in the US from both an economic and an environmental perspective. We go in depth on human versus natural cause fires and also a breakdown of fires by state. We start off by looking at the impact of wildfires on the economy. Our first set of charts show the suppression cost along with the cost per acres burned over a 35-year period. The red line depicts the mean of the data over that period of time. You can select a specific time interval, and the mean will adjust accordingly on both the charts to give you better insight. Next, we have a set of charts breaking down cost per acre of human and natural cause fires by year and by aggregated average in the bar chart below. You can hover over the data points to get the exact cost per acre burned over a given year. And one interesting thing to note is that the cost per acres burned of human fires was 64% higher than the cost of natural cause fires for cost per acres burned. Here we go in more depth, looking at multiple dimensions at the same time. We look at the days of the fire and how long it lasted, basically, and the cost per acres burned to see if there's any correlation. Each point depicts a specific significant fire, and as you hover over the point, you get a breakdown of the name of the fire, the state, the acres burned, and so on and so forth. You can zoom in to see greater detail and hone on a specific point. The chart on the right is a similar breakdown with the state on the x-axis, and the nice thing about this is that you can select a specific set of points, like let's say the Idaho fires here, and it will be reflected on the left-hand side on the other chart. Now on to the impact on the environment. So we started off with a similar set that we saw at the beginning of the impact on the economy. And in this case, we're looking at acres burned and number of fires, with the same exact functionality with the adjusted mean as you select a specific interval and move through that interval. Next, we have two more static charts with a tooltip that gives the exact acres burned and the exact total number of days per fire. This is a breakdown of human versus natural caused fires to give the reader a better sense of the fires and how the human versus natural caused fires differ. Next, we have a map of the US where all the significant fires are plotted on the map for a given year, and the size of the circle is proportional to the acres burned of the fire, so how big that fire was. The orange depicting the natural caused fires and the blue depicting the human caused fires. You can use the year slider to cycle through the years to see where the fires occurred, how large they were, and what caused them. Next, we have a bar chart breakdown of the states. The acres burned, also broken down by human versus natural, and they're sorted by the most acres burned, while also having a slider to cycle through the years to see which states had the most significant fires per year. Finally, our supporting exploration and additional analysis, we looked into the fire type count and the year over time, where our legend displays the fire type, whether it's a false alarm, whether it's severe, and you're able to select a specific type to see the trend over time. So here with severe, you don't have that many fires relative to the other types. And additional insight into further exploring the types of fires and their impact on the US.
Moving forward with our predictions navigation page. Start off for our cost prediction model. We used a data set that covered significant fires from 2005 to 2019. The significance feature within this data set that was pertinent to our predictor model was that it covered the expenses incurred for the suppression costs for each significant fire. The downside of using this data set is that the data set spans from 2005 to 2019, and then there aren't significant fires recorded within each state for each year. In order to fill in these null values, we used an imputation method, that being the KNN method, utilizing the three nearest neighbors in order to input into our model. For our model, we used the exponential time series, which is highlighted in multiple articles as being the most efficient in determining seasonal trends.
So the charts below show the predicted human-caused and nature-caused acres burned for 5 years out. And to the right, you can see a fire that grows or shrinks proportionate to a user's input. And above that, you can see the decrease the impact section where the user can input a number between 0 to 100 to decrease the percentage of human impact and nature impact on the predictions.
We implemented the same model for the cost predictions, so where the user is able to manipulate the entries at the top of both charts, and the manipulation will change the predictions for the future cost, and in terms will be visualized by the changing size of our GIF to the right. Below, we have two radio buttons that display our predictor model code, which is primarily written in R. A cool insight to our prediction models is that our prediction models just determines the cost of local, state, and federal agencies to suppress fire. The reason why we're unable to predict the total cost of a fire is due to the independent variables that are associated with the cost in terms of lost property, insured losses, and then future economic losses. And an insight into this was California's 2020 to 2021 budget, which highlighted the state's shift in strategic focus for the fires. Historically, most Western Hemisphere states have focused more into a reactive force, to where the wildland management budget was primarily split into a operational budget distribution, to where over 50% of the budget was mainly allocated to personnel and firefighting equipment, whereas to now, for instance, the state of California is shifting more into a proactive. The only difference in the new threat to wildfire is that the trend that has shifted is that, due to lesser budget allocation being allocated to land management, there has been an overgrowth in foliage, which is fuel for the wildfires. In addition, the population rate has outpaced that of the infrastructure pace, which is why we're also to accurately predict the total cost of wildfires. So our models are just limited to predicting future acres burned and then the cost of suppressing those fires.